During this session I'm going to be talking about nuclear fusion, which is the energy source for stars when it gets down to it. So nuclear fusion is the opposite to nuclear fission. Fusion takes place when two light nuclei fuse together to form a heavier nucleus. So that's where the term fusion comes from. So let me just take you through this process. Now, inside a star, I said this is relating to star energy. And stars are very complicated, and there's a huge range of types of stars out there. But I'm going to talk an example of a cooler star, a little bit like our sun, and to mention some of the nuclear fusion which is taking place inside our sun. Well, initially there'd be a big ball of hydrogen, and there'd be enough gravitational energy to put enough pressure on for the hydrogens to start colliding into each other. Now, when the hydrogens collide into each other, what happens is that they form or will start to form deuterium. Okay. They'll also release an electron, a neutrino, and some energy. As this builds, then we have the deuterium and the hydrogen colliding to create helium, and more energy is released. So then it means there's time for a build-up of helium to be produced, and at a certain strike, there's enough helium to combine with other helium to produce a helium of a larger mass and more hydrogen as well. So what you're doing is each of these stages builds up, and so there's larger and larger atoms involved. And what we'll see, and the reason why this diagram is here, is that you'll find that inside a star there'll be a whole range of these different reactions taking place, and slowly but surely larger and larger molecules building up until a final point is when we reach iron. And as iron has the largest binding energy, it is the most stable, and that will be the end of the fusion process. But as we go through that chain, all of the larger atoms up to iron, and including iron, are produced in the star forming process, which originated just with basic hydrogen. The conditions for stars, why is this so good? Well, one of the main reasons for that is the conditions are perfect for nuclear fusion. High temperature in the first place, and high pressure. The high temperature means there's high kinetic energy, so therefore two atoms, nuclei, which would be repulsed because of their similar charge, this can be overcome when they collide together. High pressure means a high density, so therefore increasing the likelihood of collision. So these two situations allow for the likelihood of a fusion reaction taking place. Okay. Looking at the reactions now. Okay. Again, there's lots of, potential options within a fusion reaction. Here's an example of one of them. The important thing here is we've got a positron and a positron colliding together to releasing energy and creating deuterium and another positron. Okay. Sometimes positrons and electrons. Let me start that again. The proton collide to create deuterium and also a release of positron. Positrons tend to not exist very long, and they're likely to collide with an electron and then annihilate themselves. But the deuteron is produced, and that's in a position which can collide with another proton. This can produce helium, and helium can likely to collide with itself to produce helium. And as we see that we have a starting from proton-proton, we have a chain reaction which builds up and goes through. And that chain reaction means that more and more energy is released. So let's think about the energy now. Again, we're going to talk about the mass deficit. So from original point we were thinking about, we have a mass of 4 protons, and in the end we have a mass of a helium nucleus and a mass of energy which is released. Now, I've shown the mass of energy emitted as 0.017 unified unit masses, or this is the equivalent of 4.36746 times 10 to the minus 29 kilograms. And remember, both of those are measurements of mass, but that's equivalent to energy when we think about Einstein's E equals mc squared. And that's the crucial thing which allows us to work out, okay, so if this amount of deficit mass is released, I can work out how much energy there is. Now, here's a typical question, looking at a question very similar to that. The first fusion of reactors on Earth are likely to be between deuterium and tritium, okay, to produce energy. Now, this is just because the amount of energy this yields is suitable at lower temperatures, so something which we could control. The reaction produces helium-4 and a neutron. So what we need to do is calculate the amount of energy liberated by this reaction. So what we're going to do is we're going to compare the amount of mass beforehand and the amount of mass afterwards, and look for that mass deficit, that change in mass, and that's going to be equating to the amount of energy which is released. I'm going to give you a chance to try and complete this question using these values. Okay, so my solution here, the first thing I'd have to work out would be the nuclear reaction, so I can show the nuclear reaction. My mass calculations, the initial mass, the final mass, and then the mass deficit, so the difference is there. Now that difference in mass is going to be released as energy, so I can do that as changing that into kilograms, and if I've got it into kilograms I can then convert that into joules, or I could consider it as electron volts, and then I've got 1.602 times 10 to the minus 19 joules per electron volt, and that gives me eventually 17.6 mega electron volts, or 2.8 times 10 to the minus 12 joules. But from the same route I've got two different answers which could be provided. Binding energies. So binding energies I've spoken about before with relation to nuclear fission. Now, nuclear fusion can also be considered by being driven by binding energies. As we see, we have iron as the most stable, and so therefore if we fuse two very light nuclei together to form a heavier one, we're increasing the stability, and by looking at the binding energies we can work out basically how much energy is being released. Okay. So we use that example. Remember that we want fusion is driven because particles want to be more stable. So here's my example question. If I use the binding energy curve to predict the amount of energy released when two hydrogen 2 nuclei fuse to produce one helium-4 nucleus. So I look at the binding energy in my products, what's going into the reaction, my reactants. So binding energy is 2 times hydrogen 2 nuclei, which is 4 times 1 mega electron volt. It's going down here. So 1 mega electron volt is the binding energy per nucleon in hydrogen 2. The binding energy in in helium, I should say, helium-4, is I've got 4 nucleon, and the binding energy per nucleon is 7 mega electron volts, so that gives me 28 mega electron volts in total. The gain in binding energy is 24 mega electron volts, and that tells me how much energy is going to be released from this situation. That should provide us a good overview